We now have all the elements in hand to present the random forest algorithm. Let's suppose that we have access to a dataset denoted Dn. We then apply the bagging procedure. We then create several bootstrap datasets. Each of these datasets results from the drawing of n observations with replacement among the n initial observations. These datasets are denoted D tilde1n up to D tilde mn, where m is a parameter of the algorithm corresponding to the number of trees of the forest. A decision tree will then be built on each bootstrap dataset. The construction of such trees is the same as that of a single decision tree, except that the splitting directions are randomized. In each cell, a certain number of directions are randomly drawn, and the splitting criterion is optimized only according to these directions. The splitting procedure is repeated until the tree is fully developed, i.e., each of its leaves contains only one observation. In particular, no pruning step is used. For a new entry point x, each tree provides a prediction noted Tnx theta1 for the first tree up to Tnx theta m for the mth tree. Here, the random variable theta1 represents the randomness used in the construction of tree 1, i.e. the randomness corresponding to both the creation of the bootstrap dataset and the randomization of the cuts within all the cells of the tree. It is therefore a high-dimensional random variable. We thus obtain m predictions, which we can then aggregate to obtain the prediction of the random forest, noted fmnx. The aggregation of the tree predictions is simply the average of the predictions in a regression problem or the majority vote in a classification problem. Here is the process of building a random forest composed of the steps of bootstrapping, building fully developed trees involving randomization of the cuts, and aggregating the predictions. Note that the trees of a random forest can be constructed in parallel because the tree constructions are independent of each other. Random forests are therefore easily parallelizable and are therefore cheap in computation time. Here is now the pseudocode of a random forest, which presents the different hyperparameters used in scikit-learn. To build a random forest, we construct a number n estimators of trees. Each of these trees is constructed in the following way. A bootstrap step is used, allowing to select with replacement max samples observations among the n initial observations. Usually, max samples is set to n. The bootstrap dataset then contains n observations. Only these observations will be used to build the tree in question. In each cell of each tree, a number of max features of directions are selected uniformly, and the splitting criterion based on the impurity criterion is optimized according to these directions only. The construction is stopped when there are either fewer mean sample leaf observations in the cell, when the cells that would result from a cut contain fewer mean sample split observations, when the cell is already cut max depth times, or when the number of leaves exceeds max leaf. By default, all these stopping criteria lead to a fully grown tree, i.e. containing only one observation per leaf. When all trees have been built, the predictions are aggregated to obtain the final prediction of the forest.